Hello everyone, you're welcome to this lesson. In this video, you're going to learn how to perform interpolation using Newton's divided difference method. Okay, so what I'm going to do is that I'm going to first of all use the linear interpolation and then the quadratic interpolation to explain the Newton's divided difference method to you. Then from there, we generate the formula for the general form of the Newton's divided difference method. Okay, so let's look at how we are going to go about this. Okay, so we are going to start with the linear interpolation. Okay, so you know that for linear interpolation, it involves two data points. Okay, so in this case, let's assume we are given two data points. The first one is x naught, y naught, and then the second is x1, y1. Okay, so what we are going to do is that we are going to fit a linear interpolant through the data that has been given to us. Okay, so one thing you have to know is that you have to take note that y equals what, f of x. Okay, and then for that reason y1 will be the same as what, f of x1. Okay, and then y naught will also be the same as what, f of what, x naught. Okay, so let's take note of that. So in general, we know that y, okay, is giving us what, f of what, x, right? So y naught will be equal to f of what, x naught. Okay, and then y1 will also be equal to f of what, x1. Okay, so let's see what you are going to do. So you are going to assume a first order polynomial function for this data point. Okay, you are going to assume that that polynomial will go through the two data points. Okay, when we do this, we will be able to generate a polynomial function that will actually fit the data point that was given. So first of all, you are going to assume, and then we find the unknown constant, then we substitute it to get the actual formula that we can use to confirm. So let's see what you are going to do. So we are going to assume that the first order polynomial function, which is the linear polynomial function, will be given as what, f1 of x. Okay, which will be equal to b naught plus b1 multiplying what, bracket of x minus what, x naught. Okay, so we're going to consider this to be the first order polynomial function that will fit this data point that has been what, given. Okay, so let's go ahead. So we have the data points. We have x naught, y naught. Okay, and then we have x1, and then y1, right? Those are the data points. Okay, so we are assuming that this polynomial function here, which is a first order polynomial function, will go through what, these two data points. Okay, so let's see what you are going to do. So we are going to have the polynomial function to be f1 of x because it's a first order polynomial function. Okay, that's what the one there means. So f1 of x will be given as b naught plus b1 multiplying what, x minus what, x naught. Okay, so this is the function that we are assuming to go through the data point. Okay, so since we are assuming that this function will go through the data point, that means that if I set the x to be equal to x naught, then we are going to have what, f1 of what, x naught, right? And then this should be the same as the y value you get when you the y value you get for that x naught data point. So that will be the same as what, f of what, x naught. And then don't forget the f of x naught will be the same as what, the y naught. Okay, this is because we are assuming that this function here, okay, fits the data point. Okay, so because it fits the data point, that means that if I pick a certain x naught value and I put it in this function, the result I'll get should be its corresponding what, y naught value. That's what this means. Okay, so that's what I'm doing here. So I'll set x to be what, equal to what, x naught into this formula here, and I'm expecting to get the corresponding what, y naught value. So that's what I'm doing here. So I have what, the f1 of what, x naught should be the same as what, f of what, x naught, which is equal to what, y naught, and then that should be equal to b naught plus what, b1, and then bracket open, our x is now what, x naught. So we're going to have what, x naught minus what, x naught. Okay, this is what we have. So when we do this, we are going to have f of what, x naught, okay, which is the same as what, y naught to be equal to b naught plus what b1 multiplying what 0, because this will become what 0. X naught minus what x naught will become what 0. So at the end we can see that what f of what x naught should be equal to what b naught. Okay, so we are going to do the same for the second data point also. So we are going to set x to be equal to what x1. When we do this, we are expected to get what y1, which is the same as what f of what x1 what f1 of what x1. So we are going to have f1 of what x1 to be equal to f of what x1, which is the same as what y1, right? And then this should be equal to b naught plus b1, right, bracket open, x1 minus what x naught, right? This is what you are going to have. So this will be the same as f of x1 equals b naught plus b1 bracket open x1 minus what x naught. Okay, so at this point what you do is that you are going to make b1 the subject. Okay, so let's look at that. So I'll take b naught to the left hand side. So you're going to have, let me continue here. Okay, so you're going to have f of x1, okay, minus what b naught, and then it should be equal to b1 multiplying what x1 minus what x naught. Okay, let me take the term on the, let me take this to the left hand side. Okay, so we are going to have b1 multiplying what x1 minus x naught in bracket to be equal to f of what x1 minus what b naught. Okay, but at this point we know what b naught is. We know b naught to be the same as what f of what x naught, so we can do the substitution back. So we're going to have b1 bracket open x1 minus what x naught, and then this will be equal to f of what x1 minus what f of what x naught. Okay, so at this point we want to make b1 the subject, so you can divide both sides by x1 minus what x naught. You can divide here by x1 minus what x naught. Okay, so this will actually cancel out this, and then at the end we are going to have b1 to be equal to f of x1 minus f of what x naught, okay, divided by x1 minus what x naught. Okay, so this is what you have. So actually b naught and then b1 are some constant values that we will need to fit into the general function, so that we can be able to find the y value of any other x value that we will choose within this data point. Okay, so now that you know what b naught and b1 is, we can substitute it back into this general formula that we have here. Okay, this is the general formula, so you can do the substitution back. Okay, so we have the general formula to be f1 of x, it's a first order, okay, to be equal to b naught plus b1, okay, multiplying what x minus what x naught. Okay, I'm going to explain to you the reason why we are saying this is a first order polynomial function. So let's continue. So let's do the substitution. We are going to have f1 of x to be equal to b naught is now what f of what x naught, okay, plus b1, which is now giving us f of x1, okay, minus what f of what x naught, divided by x1 minus what x naught. Okay, then this will be multiplied by x minus what x naught. Okay, all right, so now let's look at something here. So one thing you have to know is that when you are given the data point, you are going to know the f of x naught, you are going to know the f of what x1. Okay, you are going to know the f of x1, then you know x1, then x naught. The only variable that the only value that you don't know will be this x, right? And then when you look at this expression that we have here, if you are supposed to break it down, you are going to see that the highest power of this x will just be 1, right? It is not going to be the power 2 or 3, it is just going to be to the power of 1. So this is the reason why we call this the first order polynomial function, and then we are using it for the linear interpolation. So for the Newton's divided difference method, if you have two data points, this is how you are supposed to go about it. Okay, all right, so with this understanding, let's take an example. Okay, so let's look at this example here. The question says that the upward velocity of a rocket is given as a function of time in the table given below. Determine the value of the velocity at time t equals 16 seconds using the first order polynomial interpolation by what? Newton's divided difference polynomial method. Okay, so this is what the question says we should do. It says we should find the velocity at time t equals 16 seconds using the first order polynomial interpolation by Newton's divided difference polynomial method. Okay, so in this case, you are given the variable to be t and then velocity, okay, which is a function of what? The time. Okay, so in this case, instead of x, you are going to be using t, and then instead of f of x, you are going to use what? V of what? T. Okay, so in general, our first order function is going to be v1 of t, okay, will be equal to b naught plus b1 multiplying what? T minus what? T naught. Okay, this is what you are going to have. Okay, so now let's choose the data point. Okay, you are going to need two data points because this is a first order polynomial function. So we want to find the velocity at what? Time t equals 16 seconds. So I'm going to choose the data point 10. Sorry, I'm going to choose 15 and 20 because 16 will fall within this range. Okay, so let me choose 15 and 20. So we are going to have our x naught to be equal to 15 seconds, and then it's not x naught, sorry, t naught. You're going to have our t naught to be equal to 15. And you're going to have v of what? T naught to be equal to 362.78 meters per second, right? And then I'm going to have t1 to be equal to 20 seconds, and then v of what? T1 will be equal to 517.35 meters per second. So these are the data points. Okay, so now let's look at what you are going to do. So let's consider this general formula and then rewrite it. Okay, rewrite it in terms of what? T. Okay, so we are going to have v1 of t. Okay, you're going to have v1 of t to be equal to v of what? T naught, right, plus f of, sorry, plus v of what? T1, okay, minus v of t naught. I keep confusing myself. Minus v of t naught, okay, divided by t1 minus what? T naught. Okay, this multiplying t minus what? T naught. Okay, this is the general form of the polynomial function that you are going to have. So remember I told you that you are going to know every single value except the t. Okay, like I said, that except for the x, because we know our t1, we know t naught, we know v of t naught, we know v of what? T1, right? So I'm just going to use this to find the polynomial function that we can use for the interpolation. So let's do the substitution. So I'm going to have v1 of t, okay, to be equal to v of t naught, which is what? 362.78 plus, okay, v of t1, which is 517.35, okay, minus what? V of t naught, which is what? 362.78 divided by t1 minus what? T naught, right? So that will be divided by 20 minus what? 15. Okay, this will be multiplied by t minus what? T naught, that's what? 15. Okay, so now let's do the simplification and see what you are going to get. You're going to have v1 of t to be equal to, you're still going to have 362.78 here, okay, plus, so let's deal with what is in the bracket. So you're going to have 517.35 minus 362.78 divided by 20 minus 15. Okay, so this will give us a value of 30.914. Okay, multiplying what? T minus what? 15. Okay, so when you expand this, you're going to see that the highest power for the unknown variable t will be 1, right? And then if you have the highest power to be 1, then that's a first order polynomial function. So this is what Newton says we should do. So the Newton's method of the Newton's divided difference method is just another way for us to get what the polynomial function that we can use for the what interpolation. Okay, so the this becomes the polynomial function that we are going to use. Okay, this is the first order polynomial function. That's why I have this one here. So now let's find the velocity at time t equals what 16 seconds. That's going to be v1 of 16. Okay, that's going to be 362.78. Okay, plus 30.914. Okay, multiplying with t minus 15. Okay, sorry, our t is now 16, so let's just put it there. 16 minus what 15. Okay, so now let's simplify this and see what you are going to get. So the velocity at time 16 seconds is going to be 362.78 plus 30.914 multiplying 16 minus 15. That's just 1. So at the end you are going to get 393.694 meters per second. So that's going to be the velocity at time t equals what 16 seconds. Okay, so this is how to apply Newton's divided difference method using the first order polynomial function. So I'm going to do same thing for the second order polynomial function. Okay, so let's look at that.